Okay, reversible reactions. Now, you've been told all the way through key stage 3 that chemical reactions are difficult, if not impossible, to reverse, like burning a match or a wax candle, for example. But in reality, there are many reactions, chemical reactions, that can be reversed. This is why we need a special sign. Instead of using the arrow, we use this two-way arrow to imply that the reaction can go and does go forward and in reverse simultaneously. You're okay with this idea because with physical processes, like melting, for example, you know that if you melt something, if you raise the temperature, it melts. If you lower the temperature again, the solid will form. The same goes for boiling. If you heat up a liquid, it will form a gas, but if you cool the gas down, it will condense and reform the liquid. So, basic idea, many reactions are reversible, and sometimes it's even impossible to stop them going backwards. Reversible reactions. Now, this is a classic example of a reversible reaction. If we take copper to sulfate, it's a transition element, so transition element compounds tend to be colored. In this case, when it's got some water in it, it's hydrated, then it's blue. If we heat the copper 2 sulfate, the water that's trapped in the copper 2 sulfate escapes, and the copper 2 sulfate becomes white. It becomes anhydrous, which means it's got no water. You can see this in the diagram. This is the hydrated copper 2 sulfate. When we carefully heat it, it forms anhydrous copper 2 sulfate, which is a white solid. We can represent this as an equation. So this is the copper 2 sulfate, which is hydrated copper 2 sulfate. It's a blue solid. We heat it and it produces anhydrous copper 2 sulfate, which is a white solid, and then water is driven off. So here we would see water vapor in the boiling tube, for example. This little dot here within this formula, that dot is the water of crystallization of that solid. So it implies that this water, these water molecules, are trapped within the crystal lattice, the water of crystallization. So whenever you see that little dot, it means the copper sulfate is not only wet, it actually contains water molecules trapped in its crystal structure. Now let's keep looking at this reaction. There it is. We need to remember that we can reverse this reaction. We're talking about reversible reactions. How would we do that? We can add water to the white solid, to the anhydrous copper 2 sulfate, and it goes back. So we add the water to this and it goes back to becoming the blue solid. It's a reversible reaction. This reaction can be used as a chemical test for water. So if we've got some liquid that we think might be water, if we add it to the white copper 2 sulfate, the anhydrous copper 2 sulfate, then if it goes blue, then there's a good chance that that liquid was water. Question for you. Do you think the forward reaction is exothermic or endothermic? Now, given that we have to heat it to make it happen, there's a good chance that the forward reaction is absorbing heat. It's absorbing heat. So what kind of a reaction is it? Yes, it's an endothermic process. Now, this is yin and yang, isn't it? So if the forward reaction is an endothermic process, then the reverse reaction must be an exothermic process. It makes sense, doesn't it? If the energy is absorbed in this direction, then the energy will be released in that direction. Think back to your energy level diagrams from the last unit. Another example of this kind of reaction is with copper to chloride. There's our equation. Now this is a pink solid when it's got its water of crystallization. So it's this side of the picture. It's a pink solid, it's hydrated. And when we heat it, it loses its water of crystallization and it becomes a blue solid. We can use this fact if we absorb some of this substance onto a piece of filter paper, then when the filter paper is damp it turns pink, and when it's dry it's blue. It's called cobalt chloride paper. It can also be used as a test for water. So here, for example, if we think there's water vapor coming out of this tube, then it will turn the cobalt 2 chloride pink if it is water vapor coming out of the tube. Ammonium chloride, this is another reaction just to show you how this equilibrium reaction system works. Ammonium chloride, if we heat it, it thermally decomposes. So the ammonium chloride, which is a solid, will thermally decompose. It comes apart to give ammonia gas and hydrogen chloride gas. Hydrogen chloride gas, obviously you know of this formula when we talk about acids. So when that dissolves in water it forms an acid, but it's really a molecule. It's a covalent molecule. If we leave the ammonium chloride in a closed system, the equilibrium is reached. So all of these things exist at the same time. It's a dynamic equilibrium. All of these equilibria are dynamic equilibria. Why is it dynamic? It's dynamic because at the same time as the ammonium chloride is breaking up to make ammonia and hydrogen chloride gas, these two products are coming back together to make the ammonium chloride. So there's a constant forward reaction and reverse reaction. So it's dynamic because the forward and reverse reactions are taking place at the same rates. Why is it an equilibrium? It's an equilibrium because at any moment in time, if we look at the amounts of each of the products and the reactant, they are constant. So the amounts of concentration of the reactants and products is constant, doesn't change with time. Note, equilibrium can be reached from either direction. I'll explain that a little bit more now. Look at the reaction between hydrogen and iodine. If you start with hydrogen and iodine, they'll make hydrogen iodide. Okay, so if we start here, we've just got hydrogen and iodine. If we allow it to reach equilibrium, hydrogen iodide is made. If we started with just hydrogen iodide, then that would break up to make hydrogen and iodine. So it doesn't matter which side you start from, you will still reach equilibrium. Okay, the same temperature and pressure, the composition of the equilibrium mixture will be the same in both cases. So it doesn't matter which side we start from, and that's the point. An equilibrium can be reached even if we start with only the reactants or only the products. Okay, I hope that all makes sense. Try the questions, read the textbook, pages 116, 117, and try the questions indicated.